Okay, the purpose of this video is to review sequences and series from Magnet Advanced Algebra. So let's start by defining a sequence and a series. A sequence is any ordered list of numbers. It just has to have some order to it. The domain is the set of positive integers, which basically just means that we can have use the numbers 1, 2, 3, 4 to represent the domain of a sequence. The individual numbers of the sequence are called terms, and we separate the terms by commas. A series is just the sum of that sequence. So we have this ordered list of numbers, and if it's a series, we want to add those numbers up together to get a sum. You can have a finite sum. When we do convergence and divergence coming up, that finite sum will be referred to as the nth partial sum. You can also have an infinite series. Most of those can't be summed, although that we'll find out that there are some that can. And we just change a sequence to a series by changing those commas to plus signs to separate the terms, since we're going to add them together. So an arithmetic sequence ordered list of numbers, is a specific sequence whose pattern is created by adding a constant to generate the next term. The constant is called the common difference D. So it's a ordered list of numbers where we keep adding the same thing every time to go from one term to the next term. A geometric pattern is one that is created by multiplying a constant to generate the next term. That constant is called the common ratio, R. So you've got a pattern where you keep adding the same thing. The difference can be negative, so you can think about it as subtracting the same thing every time, or a pattern where you're multiplying by the same thing each time. R can be negative, but it has to be what you are multiplying by. You don't want to ever think of the common ratio as something you're dividing by. So all arithmetic sequences form a linear pattern. So for this example, we are just talking about how elections for U.S. president are held every 4 years, and that's occurred since 1792. So whenever you're graphing a sequence, the x-axis always represents your n. So that goes back to where it says the domain is the set of positive integers. N has to be a positive integer. That represents the first term, the second term, the third term, the fourth term, the fifth term, the sixth term. We wouldn't have like a 5 1/2 term. So those have to be positive integers. Then your y-axis is your a sub n, just represents what value that term is. So the first election happened in 1792, the second election happened 4 years later in 1796, the third in 1800, and so on. And you can see that linear pattern. From the notes that I originally posted, I changed this next example just because the example you have printed is geometric, but we didn't have really enough room to show that generated on the curve, and it was hard to see that it wasn't linear, so that's why I changed it. Because a geometric sequence is an exponential pattern, and depending on how far it's growing or decaying, it might take a few terms to actually see that develop, and the first example I had, it wasn't really a good demonstration of that pattern. So I changed the example to, on the first day of the month, you are given $1. Each day for the rest of the month, you are given twice as much as the day before. So again, your x-axis is n. This would be the first day, second day, third day, fourth day. And then I just labeled by fives over here. So on the first day, we're given $1. The second day, we're given twice as much, $2. The third day, we double that, and now it's $4. The fourth day is $8, fifth day, $16, sixth day, $32, and that pattern would continue. And you can see where that has an exponential look to it. All geometric sequences produce an exponential pattern. All arithmetic sequences produce a linear pattern. So then we have some formulas. Since it is a predictable pattern, It is possible to answer questions without the use of formulas, but those come in handy, especially for large numbers. So, for example, if I knew that the sequence starts with 10, and I want to know, and I can see the pattern, it's going down by 2 each time, then, if I want to know the next term, I don't really need a formula for that. But what if I want to know the 500th term? I don't want to have to just sit there and write out 500 terms of a sequence in order to answer that question. So I'm going to do the first couple of examples, and then you can pause the video and try them on your own. So, excuse me. Hold on one second. I thought I was a little better prepared. So these are arithmetic sequences. We're going to use this arithmetic formula. So the sequence formula is the a sub n formula equals a sub 1 plus n minus 1 times the common difference. A sub 1 always represents the first term. That should make sense, a sub 1. D, we talked about, is the common difference. What are you increasing by each time, or if it's negative, decreasing. Usually where there's confusion happens with n and a sub n. So they both have an n, so there's got to be some sort of coordination, a relationship there, but rarely would n and a sub n actually equal the same thing. N is the placement of the term. What positive integer? Is it the second term? Is it the fifth term? Is it the 25th term? A sub n is what the value of that term is. So in this example, a sub 1 is 10. The first term is 10. So n would be 1 and a sub 1 would be 10. The second term is 8. So n would be 2 and a sub 2 would be 8. The third term is 6. So n would be 3 and a sub 3 would be 6. So that's the relationship between n and a sub n. They would only actually have the same value if the fifth term was 5 or the 25th term was 25, which can happen, but not as likely. All right, so for this section, we're finding the nth term or the general rule. So basically what you want to do is take your sequence formula and you want to substitute in for a sub 1 and d, leave the a sub n and the n. So in this pattern, the first term is 10, and we can see that the common difference is negative 2 because we're subtracting 2 each time. And then we just want to clean this up to basically make a formula for this specific sequence. So you would distribute the negative 2, and then combine like terms. So your general rule for this one would be negative 2n plus 12 would generate a sub n. It's not that you can't use the original formula. This is just now an easier version that only applies to this specific pattern. So if I wanted to know the 100th term, I could just put 100 in for n and it should get my answer a little bit faster. All right, so if you want to pause the video and try number 2, since it's very similar, you just need the first term, figure out the common difference, plug those into the formula, and then do a little cleanup to get the general rule. All right, so a sub 1 is 4. The common difference is negative 2.5. You can see that it's decreasing each time. If you're not sure what the common difference is, you should be able to take any term and subtract the previous term, and that should work over and over. So it's also a way to sort of verify that that is the pattern you're looking at. So negative 7 halves minus negative 1 equals negative 2.5, and negative 1 minus 3 halves equals negative 2.5, and 3 halves minus 4 equals negative 2.5. So it shouldn't matter which term I start with. If I subtract the one in front of it, I should get that common difference. And then we're replacing in the formula a sub 1 with 4 and d with negative 2.5. I distributed and then combine my like terms. So this would be the general rule for number 2. All right, so number 3 is a little different. they gave me the first term and the 12th term. So I need to figure out the common difference, right? The two things that need to get plugged in here are a sub 1 and the common difference. I have a sub 1, not so much with the common difference. Basically, you can treat these like ordered pairs. The first term is 2, the 12th term is 46. If I needed to actually graph a sequence, that's how you would do it. And then I use basically the slope formula to determine the common difference. So 42 minus 2 over 12 minus 1 gives me 40 over, oh, wait a second, 46, not 42. I was wondering why that wasn't working out. 46 minus 2, and that's 44 over 11, so the common difference is 4. Now I have a sub 1 and d is 4, so a sub n equals a sub 1 plus n minus 1 times d. Distribute the 4 and combine your like terms. And there's my general rule for this particular arithmetic sequence. So if I wanted to know, say, the 5th term, I can quickly just put 5 in for n, find out that that's 18. All right, so if you want to pause the video and try number 4. This one's a little bit different because they actually didn't give you the first term, so I don't know the common difference and I don't know the first term, but I know I can find the common difference by converting these to ordered pairs and using the slope formula. So I've got my common difference is -3. Let's look at the situation. I don't know the first term and the second term. I do know the third term is 94, fourth, fifth, and I know the sixth term is 85. If you know the common difference, you can work yourself forward or backward into the sequence. So if I know that I'm subtracting 3 each time, then this must be 91, this must be 88, and that checks out because 3 more, and that would be 85. So I subtract 3 if I'm going forward, so I would do the opposite and go add 3 if I'm working backwards, and that'll give me my a sub 1. So now I'm able to plug in the first term and the common difference, distribute, combine like terms, and my general rule here is -3n plus 103. All right, so now we're going to do the same thing except for a geometric sequence. So we have a different formula for a geometric sequence. We still have a sub 1, the first term. We still have a sub n and n. So remember, n is that positive integer, what term we're talking about, a sub n, the value of it. And instead of the common difference, we have that common ratio, that thing that we're going to multiply each time to generate the next term. So we're going to do the same thing that we were doing before. We're going to use our formula, and we are going to substitute for everything except for n and a sub n. So here I'm given the first term, common ratio. The nice thing here is rarely is there any cleanup to do. Once you substitute it in, you have your answer, because linear pattern, there's more manipulation that can happen easily versus the exponential pattern, not so much. If you want to pause the video and try number 6 to see if you got the hang of it. All right, so I have a sub n equals a sub 1. I need to figure out what r is. So with the arithmetic sequence, if I don't know what d is, I take any term and subtract the previous term. For geometric, take any term and divide by the previous term, and that will give you r. So here r is -2/3. It doesn't matter if I do 4 divided by -6 or -6 divided by 9 or -8/3 divided by 4. And then leave the a sub n in the end. Just plug in a sub 1 and r. For number 7, I don't know the first term. I don't know r. But just like I did with this one up here where I kind of laid out the situation, I know the second term is -18, and I know the 5th term is 2/3. So I'm able to use the formula to solve for r, and if I know r, I can find a sub 1. So I know the last term is 2/3. I don't know the first term, but what I'm going to do is I'm going to pretend like -18 is the first term, because otherwise I have to manipulate it somehow. I'm trying to solve for r. If I pretend that -18 is the first term, then n would be 4, because 2/3 is really the fifth term, but I'm pretending like this doesn't exist. I'm pretending like that is the first term. So if that is the case, then this would be the fourth term, and I would put 4 in for n. If you divide 2/3 by -18, you get -1/27. And then the cube root of both sides, r, is -1/3. So if I move forward in the sequence, -18 times -1/3 is +6. 6 times -1/3 is -2. -2 times -1/3 is 2/3. So I would, if I multiply to go forward, I would have to divide to work myself back, and 18 divided by -1/3 is 54. So now that I have a sub 1, I have r. So my general rule is a sub 1 equals 54 times -1/3 to the n minus 1 power. Okay, so this first page done. Now, graph papers everywhere. I'm going to go to the second page. So for the second page, now we're going to talk about the series. Remember, that's just the sum of the terms of the sequence. So we have different formulas. A sub n is your sequence formula. S sub n is your series formula. We're still using a sub 1, which will represent the first term, a sub n, the value of the nth term, and then n is the number of terms. So if this is 10 right here, then this should be whatever's sitting in that 10th spot. If I want the sum of the first 10 terms, then this needs to be the 10th term. For your geometric series formula, we need the first term, we need the common ratio, and we need to know how many terms we're finding the sum of. This formula is more complicated as far as getting it put into your calculator and being able to not make any mistakes. But remember, it's also based on an exponential function, so you could also expect your numbers to get crazy big or crazy small and just not be as user-friendly. Okay, so let's look at some examples here. So we're finding the sum. We'll need to determine if it's arithmetic or geometric. So if you look at this pattern, it looks like we are adding 4 each time. If you're unsure, 6 minus 2 is 4, 2 minus -2 is 4, where if I do 6 divided by 2, I get 3, and 2 divided by -2 is -1. So I get the same thing consistently if I take a term and subtract the 1 in front of it. I do not get the same thing if I take a term and divide by the 1 in front of it over and over. So it must be arithmetic, where D is 4. Now, for the arithmetic series formula, I need to know what n is, and it says to find the sum of the first 50 terms, so that's n. I can see that a sub 1 is -6, but this needs to be the 50th term. And that's actually why I need to know what D is, because I need some way to figure out what the 50th term is that doesn't involve me writing down 50 terms of this pattern. So the bad news is, once you learn a second formula for these patterns, then you might have problems where you have to incorporate both of them. So we are going to solve for the 50th term using the sequence formula. The 50th term is equal to the first term plus the number of terms minus 1 times the common difference. And then we can just quickly calculate that and get that that is 190. Then we're able to substitute that back into our series formula. And the sum of the first 50 terms is 4,600. Okay, but I had to use this formula in order to find this piece of information. So generally, if you go to use one of these formulas and you're missing a critical piece of information, try going back to the other formula to see if you have enough to use that formula to find what you need for the original one. For number 2, it says it's a geometric series, although anytime they mention the common ratio, I would know that. So find the sum of the first 10 terms. The first term is 8, using this formula right here. 1 minus the common ratio raised to the n power over 1 minus the common ratio. Be careful when you're putting these in the calculator. Just make sure that, if you don't put them in, like as fractions, that you use parentheses around the fractions, those kind of things. And if you put this in correctly, you should get about 12. All right, for number 3, if you want to stop and try the next two, now is a good time to do that. For the next one, I can see that it is also arithmetic. Common difference is 5. So I have the first term and I have the last term, but I don't know how many terms I'm finding the sum of. So that dot, dot, dot means I need to find what n is. So for that reason, I'm going to have to use the sequence formula to find it because I don't know it and I need it for the series formula. So for the sequence formula, the last term is 62, the first term is 2. I don't know what term 62 is, and the common difference is 5. That's going to allow me to solve for the term. I get that. 62 is the 13th term, so now I have everything I need to solve the series formula. I'm trying to find the sum of the first 13 terms if the first term is 2 and the last term, the 13th term, is 62. And I get 416. All right, 4 is a little different. It is geometric. You multiply by 2 each time. Remember, if you multiply by 2, that's like 2 over 1. So you're just doubling your numerator. To find the sum, I need to know what n is, a sub 1 and r. I know a sub 1, I know r. Again, I don't know what n is. This time we can kind of look at the pattern though, because we can see the denominator is 3 each time, but the numerator, the first term is 1 for the numerator, second term 2, third term is 4. If you can look at that in terms of powers of 2, 2 to the 0 is the first term, 2 to the first is 2, 2 squared is 4. So the first term is 2 to the 0. The second term is 2 to the first. The third term is 2 squared. So the number of the term, the exponent is 1 less. So this must be the 13th term. So you just can kind of use some critical thinking, common sense. So I'm actually going to find the sum of the first 13 terms. A sub 1 is 1/3. R is 2. And again, just be careful when you put this in the calculator. There's a little bit extra going on compared to the arithmetic sequences. So it's 2,730 and 1/3. You do get 0.3 repeating. All right, the next thing we're going to talk about is sigma notation. That is sigma. It is a letter from the Greek alphabet. It is always meaning that we are talking about a series and we always want to find the sum. So sigma notation or summation notation you'll hear as well. So we use the sigma notation when we're talking about a series and we want to find the sum of that series. So the pattern could be arithmetic or geometric or neither. So the next lesson that we're going to have is going to be about the non-arithmetic geometric patterns. So we're going to see just a little bit of that today. So what do we do with this sigma notation? How do we use it? Well, first of all, this right here is the function to the right. This is linear because there's no exponent. So that tells me this is an arithmetic pattern. So if I know it's an arithmetic series, I know what formula I can use. And I need to know n, a sub 1, and a sub n. If you take whatever number is below the sigma and you sub that in for the first term to get a sub 1. And whatever number is above the sigma, you sub for the last term, your a sub n. Said it, but I didn't write it. And then n is always the top number minus the bottom number plus 1. Now, if the bottom number is 1, then the n value is going to be the top number, but the bottom number is not always 1. So you want kind of a formula for that. So again, I know it's arithmetic because that is linear. And for the arithmetic series formula, I need to know the first term, which I get by plugging 1 in for n. I need to know a sub n. I get that by plugging in the top number for n, and I need to know what n is, which is the top number minus the bottom number plus 1. So a sub 1 is 1 plus 3, which is 4. A sub n, which would in this case be a sub 500, would be 500 plus 3. And n is the top number minus the bottom number plus 1, which is 500. So I can do s sub 500 equals 500 over 2 times 4 plus 503. N divided by 2 times the quantity of a sub n, a sub 1 plus a sub n. So you get 126,750. Okay, so on the back, let's just take a quick accounting here. This is arithmetic again, because that is linear. This is neither arithmetic nor geometric. That exponent, that's quadratic, but that's not arithmetic or geometric, so I don't really have a formula to use for that. This is geometric because it's exponential, and this is geometric because it's exponential. So if I don't have a formula, that's fine. I could just write out all the terms of the series, especially for this one that's not arithmetic or geometric. I can start by plugging in 0. That's the first term. Then I plug in 1. That's the second term. Next, I'm going to plug in 2. Get 5. That's the third term. Then I'm going to plug in, that's 0, 1, 2. I'm going to plug in 3. Let me rewrite this. Running out of room. I didn't plan very well. This is 1, then 2, then 5. This is 10. Then I'm going to plug 4 in. I'm going to get 17. And I'm going to stop when I get to 5. So the last thing I'm going to plug in is 5. So 5 squared plus 1 is 26. Then I can just add all those numbers together and get 61. So it doesn't really matter if it is not an arithmetic or a geometric pattern and I don't have a formula, as long as the number of terms is not excessive. You would do 5 minus 0 plus 1, so there's 6 terms. I have to plug in 0, 1, 2, 3, 4, 5, generate the terms, and then add them together. If you want to pause the video to see if you can figure out the other 3, again, this is arithmetic and these 2 are geometric, but it's the same idea. Okay, so let's look at this. This one is arithmetic. The first term you get by plugging in 11. The last term you get by plugging in 30. And n is 30 minus 11 plus 1. And then because I know that this is linear, so it's arithmetic, I know I can use this formula. I've got n over 2 times a sub 1 plus a sub n, and I get 920. Number 4 is geometric, so for that formula, I need a sub 1, I need r, and I need n. So the first term you get by plugging in the bottom number. Anything to the 0 power is 1, so the first term is 2. N is top number minus the bottom number plus 1, so 11. And then for a geometric series, r should be the base to the exponent. If you're not confident of that, then just plug in the bottom number to get the first term, and then get a couple more terms and verify that the common ratio is 3. Once I get the information, though, I can plug it into my formula, a sub 1 times 1 minus r to the n power over 1 minus r, and I got my sum. Same thing for number 5. The first term I get by plugging in the bottom number. Again, anything to the 0 power is 1, so a sub 1 is 4. My n is top number minus bottom number plus 1 or 9, and r is the base of the exponent, so I can just substitute into the series formula, and you get 24.503. The last topic is an infinite series. So under what conditions can an infinite series be summed? One, we have a geometric infinite series, and we have a formula for that. In order to actually be able to find the sum of an infinite geometric series, though, the absolute value of the common ratio has to be less than 1. If the absolute value of the common ratio is greater than or equal to 1, the series cannot be summed. And then there are a few other infinite series that we can sum. We'll learn more about those when we do convergence and divergence. So you can see from these two examples, the fact that there is an infinity at the top, that's how you know it's an infinite series. And I can rewrite this 3 divided by 2 to the n as 3 times 1/2 to the n. That makes it a little more obvious that it is geometric because it's exponential. So the formula is the sum of an infinite geometric series is a sub 1, the first term, over 1 minus r. But again, the absolute value of r must be less than 1. So if you write it like this, I can see if I plug in 0, I got the first term is 3. The common ratio is the base to the exponent, which is 1/2. 1/2 is less than 1. So I can just substitute into my formula. I get a sum of 6. Over here, I can get a sub 1 by plugging in the bottom number. It would be 1, and the base to the exponent is 7/6, but the absolute value of 7/6 is greater than 1. That means there's no sum. The idea here is that if the common ratio is between 0 and 1, then this will be a series that grows towards a horizontal asymptote. So that's how come we can find a sum. But if the common ratio is greater than or equal to 1, then it just keeps getting bigger and bigger and bigger, or smaller and smaller and smaller. So we can't find a sum. It's going to grow to infinity or grow to negative infinity. All right, that's it for today. Just make sure you have your notes done. And next class, we're going to do non-arithmetic and geometric patterns.